In this section, we'll talk about the background for differential equations. Mathematical models are developed to aid in the understanding of physical phenomena. These models often yield an equation that contains some derivatives of a function. Such an equation is called a differential equation. We'll discuss two examples from calculus. Example 1 involves the free fall of a body. Newton's second law states that F is m times a. For a body falling under the force of gravity, we have that F equals negative m times g. And we also know that the acceleration is the second derivative of the position function, which I called h here for height. Using this, we obtain that m times the second derivative of h is equal to negative m times g, which simplifies to h double prime equals negative g. Now, if we integrate this equation on both sides, we get the following. So we start out with h double prime of t equals negative g, and now we're going to integrate both sides. Integrate with respect to t, and what we obtain is when you integrate the second derivative, we get the first derivative of the function, and then the antiderivative of a constant is that constant times t, and then we have a constant of integration which I'll call C1 here. What we can then do is integrate both sides one more time, and if we integrate h prime, we obtain h, and then integrating negative g times t, the t antiderivative is t squared over 2, so we get negative 1/2 g times t squared. Antiderivative of a constant is that constant times t, and then we have a new constant of integration. So what we can see, or what we actually can show, is that C1 represents the initial velocity of the object, and C2 represents the initial height of the object. So this is the initial velocity, and this is the initial height or initial position. So if we call that V naught and then the initial height H naught, our solution now becomes H of t equals negative 1/2 g times t squared plus c1t, sorry, that should be v naught t plus h naught. Another example is about radioactive decay. The rate of decay of a radioactive substance is proportional to the amount of substance present, which leads to the following differential equation. The derivative of A is equal to negative K times A. This is the proportional constant that shows that the rate at which A decreases is proportional to A. There's a negative because the amount is decaying. Now, the first thing we're going to do is we're going to divide both sides by A. And then we can rewrite it as 1 over A dA dt equals negative K, or replace this by A prime of t, and then 1 over A becomes AT here, and that equals negative K. Now, the left side of this equation is a derivative of a special function. So note, if you take ln of A of t, and then you take the derivative of that, what you end up with is the derivative of ln of x is 1 over x, so we start off with 1 over at, but then the chain rule tells us we have to multiply by the derivative of what's inside, and so we get derivative of A of t and so the final answer there is that A prime of t is this derivative over A of t. So that means that this part can be replaced by this right here on the left-hand side. So let's start out with that, d dt of ln of A of t, and then that equals negative k. So all I did was replace this part by this, and then I brought down the negative k. And now we're going to integrate both sides with respect to t. And when you do that, the integration cancels out the derivative here. So when those two cancel out, we're left with ln of A of t equals negative k times t plus a constant of integration. And then we can exponentiate both sides with respect to e. So on the left, we get ln of A of t, and on the right hand side, we get negative k t plus c. And we're going to exponentiate that with respect to e. Now here, e to the power ln of at, the e and the ln cancel each other out. So we have A of t, and on the right, I'm going to write this as e to the power c1 times e to the power negative kt. And what I'm using there is a rule for exponents, that e to the power a plus b is e to the power a times e to the power b. Now, e to the power c1 is a constant again, and one can show that that constant represents the initial quantity of the substance. So if we want to write down the general solution to our differential equation, we get a of t equals a naught times e to the power negative kt, and a naught here is the initial amount.